The last thing I want to talk about was the number 3. What was number 3? Potential due to a dipole. This fascinates me. Okay, so when you have a dipole made up of a plus charge and a minus charge, when we were doing electric fields, we found the electric field due to this dipole at this point. Like, let me go back. Right here. Now, what happens if I do the same thing for potentials? Potentials are not vectors, yes? They are scalars. So what will happen if I do that here? Okay, the definition of potential was KQ over R. So on this point, there will be a potential due to this, and there will be a potential due to that. Let's call this R plus, let's call this R minus. There's a P that goes this way. There's a D that exists here. So at point P, may I write that potential due to the plus charge plus potential due to the minus charge? What's the potential due to the plus charge? KQ over R plus. What's the potential due to the minus charge? The way I have defined this, is R plus the same as R minus? Yep. May I write this as that? So the sum of the potentials at point P due to a dipole is 0. However, the electric field, as we found above, is not 0. So there is an electric field that exists, but it does not have a potential. Now think about it this way. What we're saying is that the dipole will do no work on this charge when I bring it from infinity to this point. Let's write that down. What I'm saying is, by saying that V is the sum of the potentials is 0, what I'm saying is that the dipole does 0 work on a charge brought from infinity to this point in the XY plane. So now how do I find the potential of a dipole? Because that can't be true. Like, I could not bring anything from infinity to any point and have no work being done. So in order to do that, we have to figure out what is the force that the dipole creates at all other points beyond this point. So suppose this is D. Suppose I want to find it at this point P. So I've moved my point P for any other point. Now, in this case, what will be my R plus? What will be my R minus? and this will be my R. When we are talking about dipoles, is it true that R will always be much, much, much larger than D? The reason is because we're talking molecular scales, right? So the D, even though I've drawn it so that it doesn't look like it, but the D is atomic distance, whereas R is the scale that I'm looking at it on. So in general, for any given application, R will always be much, 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 much greater than D. In fact, if that statement is true, then the dipole is this, and the point P is that. In that situation, may I write and for my two charges, may I write at the, so let me call this point 2. At the new point P2, may I write sigma V as V plus V minus? Same thing as above. May I write this as KQ over R plus minus KQ over R minus? Now, may I write this also as KQ 1 over R plus minus 1 over R minus? May I take an LCM? R minus minus R plus. If I call this angle theta, is this angle going to be 90 minus theta? If D is much, much smaller than R, may I write R plus times R minus is almost equal to R squared, and R minus R plus is equivalent to D cosine theta. I'll let that proof be your homework. It's like literally one step. It'll be D by 2 and D by 2. Okay, so then I'm going to replace this as KQ D cosine theta divided by R squared. And what was this again? Anyone remember what that was? P. Very good. So that'll just be P cosine theta divided by R squared. So V at any other point except for the absolute middle of your dipole will always have a value, which depends on P.